Welcome to Free Body Diagram Week, and I'm going to start off by talking about this little bug, and the bug is of course sitting on the stool. And how fast is the bug moving? Just think about that, and if you need more time to think, you can pause it. And he is moving at 0 meters per second. And at what rate is he accelerating? What rate is he accelerating? And he is also accelerating at 0, but in this case, it's meters per second squared because acceleration has a squared on the end. All right, so we're going to draw free body diagrams of the bug. Well, one free body diagram. All right, so I'm always going to start representing our object by a dot. The dot represents the entire object's mass, all concentrated into the center of mass. And there is always, when you're on Earth, a force downward that is pulling the object down. And what is that force called? It is the force of gravity. And if you called that force weight, then you are right on track because that is correct. And then there's another force, because if we only had this force, the bug would be falling, right? So there's another force, and this is so weird. So very, very, very weird. Okay, there's this force going up, and it's the force of the surface pushing up on the bug, and the surface exerts this force at a 90-degree angle. And do you know what that force is called? It's called a normal force. Is that not weird or what? Okay, so this is our normal force. And I blame that name on math because in math, 90-degree angles are called right angles. They're also called normal angles. So that's where that comes from. So if you want to know more about that, ask your math teacher. All right, so these are the only two forces that are acting on the bug. So when the bug is sitting still on the stool, is the bug accelerating? No, the bug is not accelerating, and because it is not accelerating, we say that the bug is in equilibrium. All the forces are balanced, and he is in equilibrium. All right, my second example is over here on the floor. Just grab him really quickly. It is my little piñata that I got from brick and mortar school. And I'm going to take the piñata and I'm going to drop him. Woo! All right, so what symbol do we use to draw and represent the piñata? If you said a dot, then you are correct. Yay! All right, so what is the name of this force that's going down? And you can use the other example as a guide there. And if you said weight or the force of gravity, then you are correct. I should be on the video, not hiding off screen. Okay, so was the piñata accelerating as it fell? Falling object? Yes, it was accelerating, but there was a little bit of force pushing up on it, just a little bit. And what was pushing up as the piñata fell down? If you said the air, you are correct. So that's our air resistance force. That is a frictional force. It's opposite the direction of the motion and it slows it down. And we did say that it was accelerating. So is it in equilibrium? No, not equilibrium. Because it is accelerating, and when you're accelerating, you cannot be in equilibrium. We have unbalanced forces, and what is that unbalanced force called? It's called a net force. All right, example, number 3 is up there hanging from my ceiling. All right, that is another piece of art. It's a spider, and how am I going to represent that spider in my free body diagram? If you said I'm going to use a dot, you are completely correct. And then what's that downward force called? Use the other ones as examples as needed. That's your weight or your force of gravity. Now, the spider's not falling, so there must be a force balancing it. In fact, it's not accelerating because it's not speeding up, it's not slowing down, and it isn't turning. So there must be a balanced force. So I'm going to draw a force the same length as the weight going up. And what's that called? That force within a string or the force within a rope, and it's like pulling apart. If you guess tension, then you are correct. So that is our tension force. And it wasn't accelerating. So is it in equilibrium? Yes, it is in equilibrium. So there's our equilibrium examples. I have one more example to show you with my little Lamborghini. All right. This is a pullback car, so I will wind it up. You ready? 3, 2, 1. Boom. All right, so what happened to the car? Not the end. Let's talk about the beginning. What happened at the beginning? And I don't know off the top of my head how to spell Lamborghini, so I'm going to call this one the car. What are we going to represent the car with? And what do we know about the motion at the beginning? Started at 0, right? 0 speed, and then its speed increased, right? So it accelerated, right? And what causes acceleration from Newton's second law? Yes, net forces cause acceleration. And so there must have been a force pushing it forward. We're going to call that the applied force because it got applied to the car. And what's that force that always acts opposite the direction of the motion? Let's see, let's use one as an example. Oh, here's one that's backwards from the motion. And this was air resistance. What is that called in general? What's the general name for that? And if you said friction, you are correct. That is our frictional force going in the opposite direction from the motion. So are we done? Oh, yes, it is on Earth, right? So we are missing the force of gravity here. All right, so now we're done, right? Oh, yeah, well, it didn't accelerate downward, so there must be a balancing force to that one. And what is that called? The ground pushing up. So weird, so weird. What was that one called? Are you using your other examples? That is our normal force. And I'll just abbreviate it with the capital N. That's usually how it is written. So there's 4 examples. Oh, is that in equilibrium or not? Well, it's accelerating, and when you're accelerating, you are not in equilibrium. Not equilibrium, not northeast. All right, thanks for watching. Have a great week.